How do you do, ladies and gentlemen, and boys and girls? I'm Julius Sumner Miller, and physics is my business, and more especially this hour, the physics of toys again, with which we have fun abundant. Now, I call to your attention. I have done some things with mechanical toys, some things with acoustic toys, some with thermally excited, energized toys, now some electrostatic toys, a wonderful thing to witness. Here is a little box made of clear lucite on the top with a cardboard bottom, and in the box I have lodged some little figures in the shape of human figures, made of paper. Now what am I going to do? I'm going to stroke the top of this box ever so briskly but lightly with the flesh of my hand, and watch. Ah, there they are. There they are, dancing devils. Now some are sticking here, and I want to know why they do that. Look at those little rascals. Look at that. Here is one of the same substance, really. Oh, look at that. Now watch. I'm going to put my finger on the upper surface here, and this little rascal down there can do many things. He can drop down, sort of dead, or he can flip away to another place on the underside of the cover. Watch. Oh, well, oh, there, that one did it. Let me show it to you again. Watch. Oh, that one went around. And the exploration of this would take a good half hour. An electrostatic toy. Let's look at a magnetic toy. Here is an iron framework. Iron, it has to be magnetizable stuff. It could be iron, nickel, or cobalt. Question, could it be stainless steel? Answer, no, stainless steel is not magnetic, which is a very interesting thing. And here is a little lucite wheel, which has an axle, and the axle is conical shaped on the very end. Conical shaped, quite like this. So somebody says, what are you making so much of this, Professor? Well, that's it, conical shaped. Why? The physics quite profound. Now what do? I lay the wheel on there. Now what I'm going to do is the following. I'm going to put this into motion mechanically. Down, up, down, up. Now I am in resonance with the moving of the wheel. Up, down, up, down, up, down, up, down, up, down, up, down, not quite. Not quite. Now, the beautiful thing about this is this. Here is an open end, and the wheel is held there magnetically at that open end. Very amazing problem, because the magnetic force must be enough not only to hold the weight of the wheel, but to provide the centripetal force necessary to bring it around and up the track again. Or consider this magnetic toy. Here is one that is absolutely a killer to contemplate. Here is a little hollow sphere, which is loaded in the bottom with a little magnet. And you notice that mechanically it's very stable because it has a very low center of gravity. Now here is a little dog. The dog is called der Wunderhund, the wonder dog. A red one, a white one, a black one. Now as I approach the sphere with the dog, an interesting thing happens. Watch it. Watch it. Notice it spins. Let me approach another sphere with another dog. Notice this one goes away. The first one came toward me. Question, what's going on here? Well, I discovered what's going on by breaking away the front feet of the dog, and I found lodged in the front feet a little magnet. And the question is, how must this magnet and how must the magnet in there be polarized in order for these to do what they do. And in order to study that, here's what I did. I took a ping pong ball, cut it in two, put a little tacky wax in the ping pong half ball, and then a little iron sliver, which I magnetized in a very special way. And you watch. I'm afraid it may be too rough here, but watch. Yeah, get a little turning. And so I have explored it in this way in order to suggest to you how a study would be made of something you don't understand. Electrostatic, magnetic. Let me do something else. Consider the following. Let me go back to acoustics. A musical top. Here it has a spirally turned shaft, which obviously fits in a spirally turned cylinder. And when I push it down, the mechanical forces put the top in motion. And I want you to hear the wonderful music which emerges. Listen now. Listen. Isn't that wonderful? Isn't that wonderful? And I ask, how does this make such music? How do these various chords emerge? What is vibrating? I put that question for this reason. In order to have a sound, there must be some vibrating system. And I ask, the beauty in a musical top. A mechanical toy of another sort. Here is a pipe plate. Pipe plate has a lip on the bottom, ordinary. I put a stick in this corner here, and I spin it so. I say that in this position, the moment of inertia of the pipe plate with respect to this axis of rotation is very large. I give it some spin energy, which I would call in physics 1/2 I omega squared, the I being the moment of inertia and the omega the angular velocity. Now what do? I slip the stick into the middle of the disc, and a wonderful thing happens. Watch it. Whoop, fellow can lose his professional dignity here. There it is. And the wonderful thing is this, that however I incline the axis, the shaft, the disc remains in motion in the same original horizontal plane. Look at that. And notice how long the spin life, because I have given it an enormous amount of kinetic energy of rotation. One more. Wonderful thing. Classic. A little chamber, empty. No, not empty, filled with air. I put on a pumping mechanism, and I pump it up. Now I have a question to ask, which many fall down on. Consider this to be a rocket, and supposing I have some stuff in here, as I like to say, in a state of combustication. Oh, somebody says, now, Professor, you know there's no such word. Well, if I want a word, I make it. I don't like combustion. It's too quiet. I have some stuff in a state of combustication. The gases from this combustication emerge. I ask, don't the gases coming out here need the air to push against for this to go? And many people think that is so. And then I say, let us pray, because that is all wrong. This thing works best where there is nothing, because we want the gases coming out there to have the mostest stuff and the largest velocity in order to have the greatest change of momentum. So, don't ever think that the gases coming out here need the air to push against for this to go. Now I pump this up. I am putting more and more molecules of air into this chamber. I remove the pump mechanism. The gases come out this way, and this vehicle goes the other way, and I'll ask my man out here, my man Friday, to catch it. There it is. There it is. The vehicle went. Question. This is properly designed to put some water into. Question. How much water and how much air should you put in order to have the maximum efficiency? And this is a very difficult mathematical problem to engage in. Next problem, toys, mechanical. I have here a little toy duck on a string. See, there's a duck on a string, so I call it a toy duck on a string. And now you have to get a long shot of this because I want the whole thing seen. And here's what I'm going to ask. Let me hold the upper string at one position. See, it's fixed on the top of my head. And I'm going to pull down on the lower. Watch it. Oh, pull down. I pulled down and the duck went up. Now I'm going to hold the lower hand fixed on the table and I'm going to pull up. Watch. Well, now what is going on? Can I pull the duck up by pulling down, or do I pull the duck up by pulling up? In short, I want to know, what is the mechanism inside this toy duck that makes him do what he does? Or consider the classical business of the dunking duck. That is hardly ever understood, but I'm going to try to explain it quickly. Why does he do what he does? Answer. He has along inside his middle shaft a tube. He has some volatile liquid in his belly. I have wetted his head here in this glass of water. Now there is evaporation from his head. Evaporation is a cooling process, whereupon the vapor from inside his belly, which has come up into his head, condenses in this cool region into the liquid state, makes his head heavy, and down he goes. But when he gets down, the liquid runs back to his lower part, whereupon he is lifted up again. And this is the mechanism by which he works. Finally, the case of, and I'll have to step out here to do this, I guess, the case of the spheres on the strings. 2 rubber balls on 2 strings, and I trust that for you there, you have one going clockwise. Now watch it. There we are, and the other one is going counterclockwise. And I say that in order for this to be done, my hand must execute simple harmonic motion while the spheres themselves execute uniform circular motion. And thus I have mentioned the physics of the 2 balls on the strings, and I thank you for watching.